Hi students, today we're going to look at two other examples that contain a little bit more resonances than the two we did previously. We're going to look at resonances where about 3 or 4 resonances are in the 1 inch NMR spectrum, and to the side that the splitting patterns are a bit more complex than just a doublet and a triplet, a triplet and a quartet for an ethyl group that we did in the last section. So let's jump straight into it. So I'm going to start with this spectrum, and in the spectrum you'll note that just like in the previous example, we have two resonances in the methyl region of the spectrum, which indicate that these groups are methyl groups. The fact that this is a doublet indicating to 6 protons means that there are 2 CH3 groups here, and the fact that it's a doublet indicates that these methyl groups are adjacent to a CH group. So these two CH3 groups both should be joined to a CH group. That would make these two methyl groups doublet, which means that the fact that it's one resonance indicates that they're equivalent, and the fact that they're doublet indicates they are adjacent to a CH group. And the fact that it's at a chemical shift at 1.1 or so also indicates that it is in the methyl region of the spectrum, which indicates that these are methyl groups. We have another methyl group here, also integrating to 3 protons, and also in the methyl region of the spectrum at around 1.3 or 1.4. So we have 1, 2, 3 methyl groups, and this other methyl group we will find is next to a CH2 group, just like we've done previously, because this is a triplet. So I'm going to look at the rest of my spectrum now, trying to identify firstly the CH group and then the CH2 group. This CH group, if it were not next to any other substituents or non-protonated substituents, there's one more group that goes on there, and if this group is non-protonated, it would mean that this is 3 plus 3 equals to 6 plus 1. This would be a septet with the n plus 1 rule. 3 plus 3 is 6 equivalent protons plus 1, so this CH group would be a septet. If I look at the rest of my spectrum, this particular resonance, if I count it, there's a small one on that side and a small one on that side. So 1, 2, 3, 4, 5, 6, 7. 7 peaks, which would give me a septet. Which means that this would be the CH that I have here with no protonated groups next to it. So I have that particular group on there. Now I need to look at the singlet, and this integrates to 3. It's a singlet, meaning that there's no other, it's not next to any other protonated carbons. So that integration would indicate a CH3 group. The fact that it's a singlet means that it's not next to anything else. So I have another CH3 group in addition to that and that. So in my entire molecule then I have 1, 2, 3, 4 CH3 groups. 1, 2, 3, 4 CH3 groups. 2 of them are equivalent. This is in a different environment and that is in a different environment. Remember that this CH3 group that we see here is next to something which is non-protonated. And then I have the CH2 group that's next to the CH3. If this CH2 group were next to the CH3 without anything, any protonated group on that side, this would give me a quartet. So that's the CH2 group here. So I have all my protonated groups in place. I just need to see what other atoms I have involved in order for me to work out my structure. So I go to the molecular formula. I have 1, 2, 3, 4, 5, 6 carbon atoms. I've got 7 carbon atoms, which means I have an extra carbon atom. I count my hydrogens. There's 15, 3, 6, 7, 10, 13, 14, 15. All my hydrogens are in place. I have a nitrogen and I have an oxygen that I need to put somewhere in my structure. So I need to fit all these things in and give me a complete structure. If I have a carbon, there must be things on either side. I still need 2 bonds. So I need to look at this particular group, and we'll find that now I have a carbon and an oxygen. I can put those 2 together, which means I have something on that side and something on the other side. I am now going to look at my spectrum and look at all the resonances which are d-shielded, because that might give me some clue and some indication of how to join my different atoms together. The fact that this CH group that I have is d-shielded, but not as d-shielded as the other 2, would probably mean that this CH group is not directly bonded to an electronegative atom. So if I had to make a calculated guess, of these 3, these 2 would probably be more directly bonded to an electronegative atom. This would probably be indirectly bonded to an electronegative atom. So I would probably join the CH group here to the carbonyl group, indirectly bonding it to the oxygen atom. So you can see now this CH group is 2 bonds away from this oxygen, and that's why it's not as d-shielded as these other 2 resonances. So that takes care of that. I have 2 other groups that I need to put into place, and this nitrogen atom that also needs to go into place. What if I put the nitrogen atom there to make an amide, and then put my 1-methyl that's not next to any other protonated group, and put the ethyl group on the other place that's left for the nitrogen? I would then have a complete structure that makes sense. If I look at it again, that CH3 group is d-shielded because of an electronegative atom. It would probably be nitrogen. This CH2 group and is also bonded to the electronegative nitrogen, which makes sense. This CH is d-shielded but not as d-shielded, probably because it's bonded to the carbonyl group. Remember that protonated groups bonded to carbonyl groups were shifted slightly on the other side of 2, closer to 3. So normally in this region here we get CH groups next to carbonyl groups. Normally in this region here we get CH groups directly bonded to oxygen or nitrogen. So if I look at my molecular formula again, C7H15NO, 1, 2, 3, 4, 5, 6, 7 carbons, 3, 6, 7, 10, 11, 12, 13, 14, 15 hydrogens, a nitrogen and an oxygen, and this is the structure of the molecule. So that's a structure of an amide that you can look forward to. I'll do the next one in a follow-up video.